This lecture is on the quantum numbers that are solutions that were generated from the Schrödinger equation. These solutions have absolute restrictions on them, and they're representative of the energy restrictions that are in an atom. Thus, we call an atom quantized. So there's a set of restrictions that each of the quantum numbers has on each other that reflects the restrictions that the atom has in terms of its discrete energy levels. Okay, and this equation, although I'm definitely not versed in trying to work with it and come up with those solutions, you're just going to have to believe me that there are three basic quantum numbers that are solutions from this. There's a fourth that we add from the work of Pauli that I'll talk at the end. But you should understand that our electron configurations that we did last year, 1s2, 2s2, are derived from this. And we're going to explain this in higher details. But when we go through this, or when I go through this with you, I want you to understand that the quantum numbers, okay, represent numbers that each electron in an atom is unique, okay? And that's the Pauli exclusion principle. And it means that every electron will have a set of three directly from the equation itself, and of course one more that we'll add. So it's called the Pauli exclusion principle, and it means that every electron will have a unique set of 4 quantum numbers, again, that are bound to a set of rules or solutions that represent the bound different states of energy that an atom has. And Bohr stated there were 7 different energy levels, okay, through his shells of his circular planetary model. But through the solutions of this wave mechanical model, treating electrons as waves, that duality in nature we talked about, they have the ability to have standing waves. De Broglie and his electron wavelength showing that mass can have wavelength. Well, electron is just small enough to have the right wavelength that it can exist in. So these electrons exist as standing waves, and they're three-dimensional. We looked at them last year, we drew them, but now we're going to look at them a little more detail. Okay, so I'm going to leave this and go to a blank piece of paper and just write some general rules out, and then we'll go back to this and see what we're talking about. Okay, so we're dealing with, again, 3 set of quantum numbers. We're going to add a fourth in here that come directly from the Schrödinger equation that describe the electron configurations. Okay, well, we know the electron configurations. Let's say we do something called lithium. Okay, lithium has 3 protons and 3 electrons. How are they arranged? Well, if you remember last year, it is 1 s2, 2 s1. And we looked at the first energy level was filled. Okay, and we would say this is the kernel part. Okay, a part of the electrons. These are the ones that are stable. And then we have the valence, okay, and these electrons were not as stable, and they were available to do work of the bonding that's done. So we have the electron configuration that shows stable electron configurations and unstable configurations, and of course all things move towards stability. All right, what we're doing is we're describing the notation that we've used last year in more detail. This number 1 here is the principal energy level. We use that term, principal energy level. Okay, and we can say it's the n number, it's the first quantum number, and n equals 1 here. And what the first quantum number does is index size. Okay, the orbital size. And as the quantum number, the n number, okay, increase in number, the size increases. Case in point, we've learned last year that an s orbital is circular. That standing wave for an electron is a circle. And a 1s electron, okay, is smaller than a 2s electron, and so forth and so on. So the size of these places where these sublevels, I should say specifically orbital, okay, these actual shapes or orbitals where pairs of electrons can exist, okay, are 3-dimensional standing waves. Wave mechanics was the mathematics that described this the three-dimensionality of where the electrons were. And it's still based somewhat on proximity, like Bohr. Closer to the nucleus, okay, lower energy. Or in this case, we say how much energy the electron lost to get there. All right, so the size. Now, in truth, these are waves and are not easily understood. You know, here is something like the 1s orbital, and instead of me drawing it, let's go back to where I was in that PowerPoint, and let's look at the first quantum number, okay? And it indexes size, and the orbitals is the place electrons exist, given a lot of respect to Bohr by keeping that word, okay? And the first quantum number, oops, back to where I wasn't. Okay, let's go back down here. And if we notice, and this is where I wanted to show you, the 1s, 2s, and 3s get bigger, okay, as the n number increases. That's the first n. Now notice something. Quantum mechanics is based on probabilities. It's not based on singular events. It's based on statistical of a lot of different distribution of atoms. We can't say when an atom is going to give off, let's say, an alpha particle or beta particle, even if we know its half-life on the atomic level. We can just say as a group of them. So probabilities is what we use at this level. So if you look at the radial probabilities of a 1s electron, you can see that most of, or the highest probabilities to get an electron is at this distance, okay? I guess this is radius in angstroms maybe. And 2s is this distance, and 3s. And you can see that the 3s orbital, for the most part, has a lot of area in the curve that's farther away than the 2s and 1s. But it does have some penetration earlier in. So there is some, you can see the 1s is a wave and a standing wave, but it does have some area that's included in where the 1s and 2s is. But generally speaking, the 1s has a greater probability of being closer, and the 2s. And just so you know, this radial, highest radial probability corresponded directly with the radius of the atom by Bohr. So again, he was definitely onto something. All right, so the principal quantum number index is the size, okay, of the orbitals that in it. Meaning, let me go back to where I was. We're going to learn, as we learned last year, there's many different orbitals. Like if I'm in the 3s orbital, okay, and I have a certain size to that, generally speaking, the rest of the orbitals in the 3 are about the same size. They differ slightly, okay, but they're all basically fit within this sphere, even though the types of orientations in orbitals change. So size is based on this number here. Now, what makes, let's say, a p orbital have more energy, even though it may be just as far away as an s, is its difference in its specialty in its shape. Being having electrons restricted to this shape requires a little more energy, even though they may on average be the same distance away. So even though we said distance and proximity was what Bohr used, and it's still true somewhat in this model, now that we look at the peculiarity of the shapes, it takes a higher energy for electron to exist in a shape that's more irregular, if you want to think of it that way. So this would fit, this p orbital fits into the s orbital, okay? It's a little different that we dealt with last year. And electrons in this p orbital have a higher energy than an s, well, because of that uniqueness to the shape. Okay, so the first number here in index is size. Okay, well, the second number, okay, tells you the sublevel that electrons exist in. Now, the sublevel is an actual three-dimensional shape. We know S's are spherical. We know P's have this dumbbell shape. Okay, now knowing that, this is solved for in the Schrödinger equation by looking at a quantum number called L, sometimes called the angular momentum a quantum number. Okay, now this number defines S. Okay, the N defined the one here. This L number defines these shapes, SP, and we have a D, we have an F, and we have G's, and it continues on theoretically. Now, how do we define these shapes? Well, the mathematics, the quantum mechanics defines this quantum number, which defines your shapes, okay, as preferred axes. So this indexes this quantum numbers the preferred axes. And what does that mean? I know I had some trouble talking about that. Well, a sphere, what's preferred in a sphere? Which axes? There isn't any. An S doesn't prefer any axis, it's a sphere. But if you look at a dumbbell-shaped p orbital, it's preferring one axis. There's an axis. Okay, well, and again, a circle, well, you can draw the axis here, the axis here, the axis here. There's no preferred way to draw something that will intersect the entire orbital through its middle. And that's kind of my own definition of axis. So you get that. You can draw a radius any way you like through this s orbital. Here, this is the best way to intersect all points as equal as possible. Here, there's no preferred way to do that. So that's my answer to you, whoever had that question. D orbitals, because they're more complex shape, have more preferred axis in G and so on. So this number indexes the preferred axis. Let's look at its restrictions, okay, on the next page. Now we know that n can be 1 through 7, and certainly we think 8 and 9 maybe are a possibility, maybe if the equipment is right and we can detect them on a small letter, because they're going to be very unstable in that area. If we're talking about period 8 and 9, there's no elements on that period table, and some people think there may be some theoretically. Okay, so even though I do say 1 through 7, you know, there are some certain island of stability type of elements that could exist. Possibly, we don't know here, but the periodic table 1 through 7 is basically what we're starting with. So n equals 1 through 7, index is size. Okay, this number, the angular momentum number, okay, is indexed by preferred axes, as I just talked about. Now, it's restricted, okay, by the n number. As the size gets bigger, we're able to have more complex structures. It's just that simple. So complex structures can't, or complex orbitals of shapes that are more complex than, let's say, a sphere of an S, only occur in bigger orbitals. So the type of orbital and how many is indexed by the n number. So we have this range of n numbers, and we go 0 to n minus 1. That is showing us the range of orbitals. Okay, this tells us really how many orbitals. Oops, that didn't work out. Let's go back. How many orbitals and what type. All right, so how many orbitals, I'm sorry, how many sublevels, bad Grotsky, good pizza. So how many sublevels, and of course the type, the shape, okay? All right, now let's go back to a thicker pen. I didn't like that. All right, so what does this mean? Well, if n equals 1, what is my angular momentum number? Well, I put this 1, of course, here, and I solve for it. I get 0, 2, of course, 0, which gives me just one quantum number. L here is equal to 0, and a 0 is equal to an S sublevel, which is a spherical sublevel. Now, why is it 0? It has 0 preferred axes, as we talked about. Now, when n equals 2, okay, let's plug it in. You put this 2 in here, and you get 0 to n minus 1, 2 minus 1 to 1. So 0 to 1, which means you have a range of 0 and 1. These are the possibilities of sublevels at the second major energy level. And that means you have an S, that's for your 0, and you have a P sublevel, that's for your 1. Now, of course, S has no preferred axes because it's a sphere, and of course a dumbbell has one preferred axis. Okay, so as we move on, we'll see that n equals 3, okay, and you plug that into 0 to n minus 1, and you get 0 to 2. So in this third major energy level, principal energy level, you get a range of possible, okay, I say possible because it depends if you have enough electrons to go in there, but the possibilities for n equals 3 is 0, 1, and 2. Okay, and what does that mean? Well, that means that in the third energy level, we have S, we have P, and the d orbitals, which I'm not going to try to draw. Here's one possibility of a d orbital, that donut ring around. Yeah, okay, any case, the d's have two preferred axes that you could intersect if you use my basic definition. All right, and then when n equals 4, you have 0, 2, 3, right? N minus 1, okay, will give me 0 to 3. So the possibilities at 4 are 0, 1, 2, and 3. And the 3 sublevel, of course, is that F sublevel, okay? Which makes you think, hey, I only know about F sublevels last year. Okay, and let's take a stop here and look at something I gave you last year to look at where these sublevels are. Okay, so we can see that 1s, 2s, 3s, 4s, here's the S block, the D block, the P block, and the 1s block. So when we were writing configurations last year, okay, we said 1s2, 2s2, 2p6, 3s1, 3s2, and this gave us a descriptive place. We noticed that the 3d came after the 4s, there was overlapping, and the 4f hooked up here right in this area, okay? So it detoured right in here. So we learned how to do all of this last year, and we will review this. I'm just showing where the numbers come from, but we don't see any G's. Okay, well, G would kick in, if you remember, in the 8th sublevel. So even though we see that there's a possibility of a G in the 5th energy level, because if you have, okay, a quantum number, let's get back to this. If you have a quantum number of n equals 5, that means L's possibilities are 0, 1, 2, 3, and 4. Well, who has 4 preferred axes? That would be a G sublevel. Okay, and hey, let's take a look at what that might look like. Okay, so hold on. Okay, so before we look at the G's, what they might look like, here's the dumbbell shape that I was talking about, drawn a little differently, 1 preferred axes. Okay, and you're showing 3 orbitals. We'll get that to a second. And then we have our d orbitals, okay, a little differently drawn, a more complex shape with 2 preferred axes. And then we have our f orbitals, which have the the 3 preferred axes. And then, of course, we have the theoretical. That's not theoretical. Electrons can exist there if they're excited. Okay, the g orbitals. Okay, and these are mathematically shapes defined by the wave mechanics model. Okay. All right. So as I said, n equals 5. The possibilities you can have 1, 2, 3, and 4. Okay. So that's, again, you can't have an F in the second. You can only have F in the third because of the restrictions that we have, and these restrictions are these rules that are born from the solutions to the Schrodinger equation. So these restrictions I'm talking about is restrictions also in energy. So that is the azimuthal number. That is sometimes called the azimuthal number, but it's also the angular momentum number that indexes axes, preferred axes. Okay? All right. So the next number and the last number is the magnetic quantum number m sub L. And this indexes, all right, and this is important. And okay, hold on. That's just a dryer. Okay, hold on. So again, m sub L index is orientations. Okay, in the preferred axes. All right. Okay, remember the L number just measured how many preferred axes. Now we have orientations in these preferred axes. So what does this mean, this orientations in the preferred axis? This means the actual number of orbitals. Orbitals, and the word was derived somewhat from the Bohr model, the orbits, to give Bohr a lot of credit for what he said. This quantized model is still a quantized model when the electrons are behaving or acting as waves or wave functions. So that's what they did. But orbitals, or a place where a pair of electrons exist. And we drew boxes last year for notations. We also drew some of the shapes in one of those labs. But orbitals, okay, how many orbitals? How many pairs? Well, how many orientations in that preferred axis? Let's go back to our, let's get away from the g orbitals. Let's get more realistic. Okay, well, let's go back to the s orbital. Okay, in the s orbital, with one preferred axis, there's only one orbital. Zero preferred axes, sorry. There's only one. So one of these holds 2 electrons. Okay? The p orbital has 3. Has 3 orientations over one preferred axis. Okay? A d orbital has 5 preferred orientations. 5 orbitals. We knew this last year. The d block has 10 electrons, and we said, hey, 2 electrons exist here, 2 electrons exist here. Okay? The f orbital has 7 orbitals that fill its sublevel because 14 electrons, 2 apiece, but more importantly, the 7, there are 7, okay, orientations around its 3 different preferred axes. It gets complicated, and of course, when I go G, you got a bunch, and I'm not going to get into that, all right? And of course, there are some others that you can look at. So that's where that comes from, but how do we come up with the actual number of orbitals? Last year, sorry, we went here and said, hey, the d block has 10 what? 1, 2, 3, 4, 5. You believe me, there's 10 columns. There's 10 electrons, and electrons pair up, so there's 5 orbitals. There are 14 electrons in the f block, so you would have 7. P has 6 total electrons, so it had 3. S has 2 electrons, therefore it have 1. But that's not how we get it. We get it from the restrictions, or I say the solutions, derived from, or in parts solved from, the Schrodinger equation. So how do we do that? Well, very simply. We know that n has a restriction. It's 1 to about 7. Then we had L has the what? Has the 0 to n minus 1. And now the m sub L quantum number is equal to negative L, okay, whatever you need to do to get to 0, and then back to positive L. Let me explain. If I put an S to this solution, so let's say n equals 1. All right, putting into this restriction, I get a 0 to 0. That means my L is 0, which we now know is an s orbital. Put this 0 here, and you get a 0 to 0. That means my m sub L is 0. And what does that mean? That means how many, I can't say integers, is a 0 an integer? I'm not really sure, but how many values do you have here? You count just 1. So in the first energy level, there's an s orbital, and there's only one of them. Okay, let's do n equals 2. N equals 2. I have 2 angular momentum numbers. I have 1. So I have 0 for the s and 1 for the p. If you put that in, it's 0 to n minus 1, so 0 and 1. Now the m sub L number can be what? Well, if you do for the 0, it'll come out to be 0. So the m sub L number that comes from here would be 0. But if you deal with the electrons in this p orbital, well, then you're going to have this. Put a 1 in here, negative 1 through 0 to positive 1. Count how many different scenarios you have. You have 1, 2, 3. This would give you 3 orbitals. Okay? And that's how that works. Remember, it gets a little confusing here because we're talking about quantum numbers for one electron. Now, let me try to make this very clear. Let's change inks because I can. Okay, let's go to red. Now let's look at a 1s2, 2s2, 2p1. Okay, and that would be boron. Okay, so boron, okay, has 5 electrons, and that's how the electrons are arranged. Now, I want to know what the quantum number is for that particular electron in that p orbital. Well, the first thing is n equals 2. That's easy. Now, this p orbital means, excuse me, so look up here, n equals 2. You have two possible scenarios for L. You're going to have, like we just talked about, you're going to have either 0 to n minus 1, you have 0 and 1. Those are the two quantum numbers that we have for sublevels. Okay, well, that tells us that we can have an S or a P. But since I'm talking about this particular electron, the angular momentum number is equal to 1. I know there's another one there, but I'm talking about just about this electron. So it's in the P, the N is the L is 1. Okay, now, what else do I have? Well, the magnetic quantum number, okay, m sub L, if you put this 1 in, you get a negative 1, 0, and guess what? You have three possibilities. You have negative 1, 0, or plus 1. So there's three different orbitals. Now we don't know which one it is, so I would say negative 1 first to show that we're in the first orbital. Now, if I write this out for the P, you would see that P has three boxes. Each box is the three orbitals. This could be the negative 1 orbital, the 0, and the plus 1. I hope you see my drift here. P has three possibilities, and since electrons fill lowest energy orbitals first, we'll say negative 1. We're not really sure which one it would be, but there's three. Let's look at something else. Let's look at scandium for a second. Let's just clear this. No, let's do it over here. Let's get rid of some stuff and do scandium. Okay, change my inks because I can. Okay, scandium, all right, is 1s2, 2s2, 2p6, 3s2, 3p6, and it's 4s2, running out of space, and then 3d1. Again, we're going to go over all this stuff again, but the 3d1, there just should be a 1 above here. I want to know the quantum number just for that. Okay, well, the n number is 3. The angular momentum number has three possibilities, doesn't it? Okay, if I put 3 in this formula, okay, I'm going to get 0, 1, and 2. So I have an S, which I'm not talking about, a P, and a D. So the D would be 2 when I solve for that. Now the M sub L has a bunch of possibilities, doesn't it? Put this 2 in this formula, negative 2 through 0 to positive 2. Well, what's that going to give me in this case? It's going to give me negative 2, negative 1, 0, plus 1 to plus 2. How many different scenarios is that? You guessed it, 5. 5 different orbitals. So this 3D1 will say negative 2. And if you had 3D3, okay, we would talk about something else. So that's how you get the three quantum numbers. Now there's one more quantum number, okay, and that is from something called spin. Okay, electrons, if you note in orbital diagrams, are written like this with opposite spins. And I'll talk about this. But for all intents and purposes, we're going to say plus 1/2 for the one that goes up and a negative 1/2 for the one that goes down. Electrons exist in two orientations, okay, and we'll say plus 1/2. So in this case, for this electron, we'll do m of s, the spin, to be plus 1/2. You wouldn't know if it was negative 1/2 otherwise. And this one, okay, would be, again, m sub s plus 1/2. So those are 4 quantum numbers. I'll define this spin for you in class. Okay, so every electron you see here will have 4. Now, when will you have the negative half? Because I'm giving you. What if I had 3, let's look at 1s2, a brand new page. Last one, and I promise I'll be done. So 1s2, helium. Okay, n equals 1. L is equal to 0. M sub L has to be 0 based on our rules. Now, there's 2 electrons. If I draw orbital notation, this is orbital notation, you would see this. Well, this electron, that up arrow would be m of s equals plus 1/2. This electron has to have a unique set of 4 quantum numbers. N equals 1. L is still 0 for s. And m sub L is still 0 because there's only one orbital or one orientation for that possible s. and the m sub s would be negative 1/2. So every single electron, this would be the electron that for the first electron in helium, this would be the 4 quantum numbers. Okay, so that should be good enough to understand how to do this. Okay, and so when I ask for the homework, please use the restrictions on the opposite page of the homework I gave you. I gave you the rules, but just be in mind that those rules really represent restrictions, and every one of these quantum numbers depends upon the restrictions of the other rule, because electrons are quantized. There's a discrete amount of energy, well, there's a discrete amount of certain shells, or I should say standing waves, electrons that can exist. Okay, take care.